Hello guys, I'm Professor Mark Tulio with Fundamentals of Mechanical Vibration. Today we're gonna solve a problem whose the goal is to write equation of motion of a pendulum with disc connected to its free end rolling on a cylindrical track by using Newtonian mechanics. So let's go. Well, the system is composed by a bar connected to the fixed pivot, and its free end is connected. On its free end is connected a disc, and the disc rolling on a cylindrical track, as you can see here. There is no slip. This is a picture to show some parameters for this problem. Here, vertical dashed line, we have the equilibrium position, the radius for cylindrical tracks capital R, the angle theta is used to describe the motion of the bar, the angle phi is used to describe the motion of rotation motion of the disc, the rate of the disc is R, the mass of the bar M, the mass of the disc capital M, the contact point between the disc and the cylindrical track is point A, the center of the disc is point C. Just for information, the point A is the instant center of rotation due to the rolling motion. Okay, so the bar length is L equal to capital R minus R. It's necessary to know what's the kinematic relationship to couple the variable theta and the variable phi. Let's remember that the system has one unique degree of freedom. For this reason, we need to find a way to couple both variables. The tangential displacement of the center of the disc is common if you see this motion from the point A or from the point O or from the point A. As you can see, analyzing this triangle here, look, the tangential displacement seen by O is the same than the seen by point A. Now, this left-hand side of this equation here represents the tangential displacement seen by O, and the right-hand side the tangential displacement seen by the point A. If I isolate phi, we obtain this expression here. Why? We need to write the equation of motion with respect to theta. Let's go on. We need, because we are using Newtonian mechanics, we need to draw the free body diagram. The free body diagram for the bar, we need the bar in that position here. This dashed line means the radial direction, the point O, the point of rotation. The vertical dashed line is the equilibrium position. From this equilibrium position, we describe the angular motion by using theta, and the weight of the bar applied to its center of gravity is here. Now we have the reaction forces and along the radial direction. In this case, the bar is in tension. Is tensioned, yeah. At the free end of the bar, there is a tangential force. Okay. Now we need to draw the FBD number 2 for the disk. Here's the disk, the angle phi, the reaction for the radial force, the weight of the disk, the reaction for the tangential force here applied to this at the center of the disk, the normal force due to the contact, the point C, the point A, the rolling friction force here. In this case, let's recover important information. In this case, the bar drives the disk. For this reason, the bar rotates counterclockwise and the disk rotates clockwise. As the disk is driven by the bar, the orientation for the rolling friction force, it's pointed as you can see here. Okay. Now we need to know the moment arms. The first moment arm is related to the center of gravity of the bar, as you can see here. 1/2 times L times theta. The same way for the disk. L times theta. And the last one, we need to know the moment arm about A, between the weight of the disk here and the point A, because the rolling motion. In this case, this moment arm here is equal to R times theta, this distance here. So it's time to apply the second law. So let's go on. For the FBT1, we need to consider the rotation about the point O. The counterclockwise is positive, according to the free body diagram. In this case, sum of moments about O is equal to mass moment of inertia of bar about O times angular acceleration. The first term here is the moment due to the weight force, the bar. The minus is because the moment generated by the weight force here rotate the bar clockwise, but in this case the counterclockwise is positive. For this reason, you need to put the minus here, the force times moment arm here. The same way for the tangential force here applied to the free end of the bar. The moment arm for this force here is the L itself. Okay, is equal to mass moment of inertia times angular acceleration, theta double dot. We obtain this expression here. Tangential force is equal to minus 1/L JO theta double dot minus 1/2 mg theta. Now we need to apply the second law for the FBD2. In this case, is a rotation, instant rotation about point A, because the pure rolling motion. Now the reference is counterclockwise positive. The sum of moments about A is equal to the mass moment of inertia of the disk about A. If we proceed, the moment generated by the tangential force can be calculated as tangential force times R. Positive because agree with this reference here. Minus because the moment generated by the weight of the disk, minus capital mg times this moment arm here is equal to this expression. Let's remember that the phi can be written as this expression here. We need to replace the phi double dot to write all of the equation with respect to theta. Here we have phi, but here we have double dot phi. Just put double dot over the theta here and replace this expression over here. Okay? And so we get another expression, a second expression. Now we need to equate both of expressions here, because in both expressions the tangential force is already isolated. So let's go on. We get this expression, and if we rearrange this expression here, we obtain a third expression. It's a boxed expression here. Before we go on, we need to discuss very, very important concept here. The concept of the mass point. So let's remember that the disk can rotate freely at the free end of the bar. There is no friction here. Okay? There is no friction. For this reason, as a rigid body, the disk does not contribute to the system as a rigid body. However, the disk contributes as a mass point. Okay? But there is no reason for worries, because this information is already implicitly incorporated to the solution. Okay? No worries. So let's go on. Now we need to I really forgot to show you the mass moment of inertia here, JA and JO, need to be calculated. Okay? Let's do it now. The mass moment of inertia of the disk about point A, about point 8 here. To do it, we need to use the parallel axis theorem, also known as Steiner theorem. It's mandatory in this case. Why? Why? The point of rotation is not coincident to the centroidal or CG mass moment of inertia. So for this reason, we need to transfer the inertia from here to the point of rotation. The mass moment of inertia of the disk about A can be calculated as its mass moment of inertia about CG, its CG here, sorry, plus its mass times squared R. Why R? Because R is the distance between the point A and the point C. Now we obtain the mass moment of inertia about A. The same way to the point O. We need to calculate mass moment of inertia of bar about point O. This first term here you can find in an ordinary table for the mass properties. For the homogeneous bar, we have 1 over 12 times mass of the bar times squared L plus its mass times the distance between its CG and the point of rotation. In this case, as we have a homogeneous bar, the CG is located at the midspan, like as you can see here. Now, finally, we obtain the mass moment of inertia of the bar about O. So, it's just replace the both inertias here in the third expression that we obtained in the last slide, in the previous slide, I'm sorry. So from now on, it's just to be careful with the algebraic work here, just to proceed. If we proceed, we obtain the equation of motion for this system here. But if you want, you can go on here to read other fashion for this equation here. All this term multiplying the theta double dot is our equivalent mass, and all this factor here multiplying the theta is the equivalent stiffness. So we can rewrite this equation here in another fashion. If we divide all the equation by the equivalent mass, we can obtain another fashion for this equation. So finally, we have the last level of this equation. Just discuss this term here. The term multiplying theta is the squared natural frequency. So all this term between the brackets here is our natural frequency, squared natural frequency. So the natural frequency is pointed here, okay? So guys, I hope you enjoy this video. Please subscribe the channel, share this material, and see you on next video. Bye.